Good evening, everyone. Welcome to our first Cosmic Thursdays virtual lecture series in 2021. Happy New Year. My name is Sinan Du, and I am in charge of the education and public outreach in the Department of Physics and Astronomy at UC Riverside. I am also the organizer of this event. We're very grateful that you're here with us at this virtual lecture. We warmly welcome all the newcomers and also very excited to see a lot of returning attendees. So today it is my pleasure to introduce our speaker, Dr. Varoujan Gorjian from the Jet Propulsion Laboratory, or JPL. Dr. Gorjian got his PhD from UCLA in astronomy and astrophysics, after which he joined JPL as a research associate and has been working there since then. He has been on multiple science teams and also working on astronomical observations, especially use infrared light. He has been the education and public outreach lead for the Spitzer Space Telescope as well since 2006. So in this lecture, Dr. Gorjian will be reviewing JPL's history from the very beginning and how it has evolved into becoming one of the NASA's key centers for robotic space missions. So everything's going to be very exciting. Finally, I'd like to thank our lovely volunteers today. We have 4 solar system ambassadors joining us in the live chat today. They are all space enthusiasts and have been trained by JPL on communicating NASA's exciting discoveries and plans for future exploration of the solar system and beyond. So I will now call their names and have them introduce themselves a little bit. So they are Christine Hurst.
Sorry, I was muted. I'm sorry about that. I won't do that in the real deal. Hi, I'm Christine. I'll introduce myself for 30 seconds and next person. Do you want me to actually introduce myself?
Yes, yeah, this is already live.
Okay. Awesome. Hi, I'm Christine, and I am an astronomy educator in Southern California, and I teach community college, and I'm teaching for the NASA Endeavor program, and I am obtaining my PhD in astronomy education at UCSB.
Great, thank you, Christine. And next we have Elena Semerjan.
Hello, everybody. Thank you so much for joining us today. My name is Elena Smerjan. I'm a NASA Solar System Ambassador, as well as a Glendale City Commissioner in Los Angeles County for the status of women.
Great, thank you, Elena. And then we have Jeff McKeeven.
Hi, I'm Jeff. I'm a Solar System Ambassador, and in my spare time, I also work at Griffith Observatory as a museum guide. I'm going to now go hang out in the chat with y'all. If you have any questions, just let us know.
Thank you, Jeff. And finally, we have Emmanuel Mesanson.
Hi, everyone. My name is Emmanuel. I work at UCLA in the Experimental Space Physics Group. And we built a satellite that studies Earth's magnetic field and the radiation belts and the aurora. And it's been in orbit for a couple years now. So we work on that. We also work on other space weather topics, the interaction of the sun and the Earth. So flares and CMEs, explosions, that sort of thing. But yeah, I'm happy to answer questions about the moon too. So we have a couple satellites we operate around the moon. So
great, thank you. And I also like to mention that there's a UCR astronomy graduate student, chat moderator, Brian Scott, who you cannot see at this moment in the Zoom meeting, but he's already in the live chat to take your questions. So Brian, feel free to introduce yourself in the chat. All right, so all our chat moderators will be moderating the live chat that you can see on the right-hand side. We welcome all kinds of questions and also encourage you to engage in discussions. The volunteers will be answering most of the questions and also passing the other ones to the speaker as we go along. All the questions for the speaker will be answered at the end of this lecture. And since we have a large group today, as you can see, we kindly ask you to be respectful to others in the chat. So without further ado, take it away, Varoujan.
Okay, well, let's share the screen and make sure everybody can see what I'm hoping everybody can see. Is everybody seeing the presenter view, I hope? Not the presenter view, I mean the actual view.
Yes.
Okay, great. Thanks everybody for joining. I love doing astronomy, I love doing the science, but I also love the history of how whatever group and institutions that we have do that particular science. And working at JPL, I've started looking into the history of it, and I think it's a fascinating history because it's one of those things that there's a lot of things that happen which you would not have expected would have happened. And like most of history, there are interesting twists and turns, and hopefully that'll get you interested not only in the science that came out of it, but also just the fact that whenever you think who is the right person or who should be doing science or who did the science the right way, is almost never what you expect it to be. So let's start. So we go back to the 1920s and 30s. So this is the time when finally there's, the engineering of making rockets was actually getting to the point where people could think about making rockets, but rockets was primarily an amateur pursuit. That is, no professional organizations, no engineers, no scientists, they did not engage in it because this was science fiction. It was from pulp magazines like the image you're seeing there, from comic books, Buck Rogers, Flash Gordon. By the way, at the time it was known as scientifiction, and so it was not something that serious people would pursue. So it was entirely amateurs doing it, and there was enthusiasts, and it was worldwide. And without having a World Wide Web, there was the Worldwide Post Office. So they would actually do their experiments and write letters about them, and write letters to different groups and ask questions. How did you solve this problem? We did this, we had this success, and so on. So but again, it was not done by the professionals. So into this arena walk two teenagers from Pasadena. One is Jack Whiteside Parsons on the left there in that image, and then his friend Edward Foreman. They were friends who attended John Muir High School together, and they both worked on fireworks, and then they started working on rockets, again, as an amateur, hobby pursuit kind of thing. They worked at a place called the Hercules Powder Company, and then later at Halifax Explosives. And so they were actually gaining real experience in building things that would explode. And of course, that's what they needed for their rockets. Of course, a much more controlled explosion. So that was the institution that was at the university that was in Pasadena was, of course, the California Institute of Technology, known as Caltech. And in 1937, they both went to a talk given in the aeronautics department, and they met a man named Frank Molina, who was a graduate student in the aeronautics department. First of all, it was very unusual to have any talks on rocketry in any reputable aeronautics department. So that was unusual. So they went there, they met with Frank, and and Jack Parsons thought it'd be great to sort of combine their practical expertise with the more theoretical expertise that the people at Caltech had. So they went to the head of the aeronautics department, a man named Theodore von Karman, and to ask if they could, give him some space and some money to help them do rocket experiments. And von Karman said, sure, and he gave him some funds and some lab space for them to do their rocket experiments on the Caltech campus. But it was not smooth sailing because another Caltech professor, actually a very well-known astronomer named Fritz Zwicky, who is one of the first people to notice that there was a lot more mass out there than light. So this is what we would eventually start to call dark matter. He actually coined that term. So he was a very heavy, scientist, and he'd come to Caltech, but Caltech at that time was relatively new. It had just become in the 20s, switching from this group Technical Institute to becoming Caltech, sort of mirroring the Massachusetts Institute of Technology on the West Coast. And so he was very upset at supporting rocket research, and he went to von Karman and told them, what are you doing supporting rocketry? We're trying to establish ourselves as legitimate scientists and engineers, and you're supporting something that's completely disreputable. Fortunately, von Karman didn't think that, and he didn't have to listen to Fritz Zwicky, and he didn't. Not many people had that luxury, but he had, and so he allowed the experiments to continue until, as you might what happened, as you might think, what would happen with rockets, you had explosions, they had various other issues, and so it ended up being that they were encouraged to leave campus and look for a different place to do their experiments. So they went off a sufficient distance to be away from campus, not to bother anybody, so it wasn't very inhabited, but they couldn't be so far because they had a lot of equipment that they had to lug out all the time. And so they went to a place called the Arroyo which is, if you're driving on the 210 freeway through Pasadena, you will pass by it, as there's this jog that the 210 takes and shifts as it splits to the 134, you will pass by the Arroyo Seco, and that's where they started doing their experiments. And in fact, they got many people to join this group. They named themselves the Suicide Club, partly because of all the explosions, but then this is where they started doing their experiments, and in fact, where the Jet Propulsion Laboratory stands today. And it's a really critical thing to sort of point out at this point, because what was reputable research was jet engine research, and what was disreputable research was rocket engine research. And the difference between the two, if people aren't familiar with it, is how you achieve combustion. In both cases, you have combustion. And to have any kind of combustion, you have a fuel, and you mix it with an oxidizer. And that oxidation process is what gives you this combustion. So with a match, obviously, you bring it enough heat, and the fuel usually is, the wood of the match, but then you have a little bit of a spark from the tip of it, but then that mixes with the oxygen in the air. Oxygen is a pretty good oxidizer. And that's how jet engines work. They take air from the atmosphere, combine it with their fuel, heat it up, obviously they combust it, and then they put it out behind the jet engine, and that moves the plane forward. I've oversimplified things greatly because it's not just simply the gases coming out. The gases actually turn other turbines and so on and so forth. But fundamentally, to achieve the combustion that runs the jet engine, they need the oxygen to come from the air. The difference with rockets is that the oxygen, or actually the oxidizer, is carried along with the fuel in the rocket. So you don't need air. That's why rockets can operate in space. Rockets can operate underwater. So the point of it is that you have the oxidizer, often liquid oxygen. You mix it with some sort of fuel. It could be liquid hydrogen, it could be liquid methane, or whatever. And now you have fuel plus oxidizer, you ignite it, you achieve combustion, hot gases are created, and they're thrust in one direction, the hot gases go one way, your spacecraft or rocket goes the other way. So in the 1930s, jet engines were legitimate areas of engineering research, rockets were not. So the US Army Air Corps at the time had the idea of attaching small rockets to their propeller planes that would help them take off on short runways or very quickly built runways, which is what happens during any kind of war that's coming up. And so quickly built runways aren't as smooth, and so it slows things down. So you need that extra oomph for your plane to take off. But so they were very much not interested in being seen as supporting rocket research because it was too science fiction-y and disreputable. So what they wanted was rocket-assisted takeoff. But that's a RATO if you try and reduce it to an acronym. But they wouldn't call that RATO. They called it JATO because they falsely, but to cover things up, called things JATO units, jet assisted takeoff units. And that's what they came to Caltech and to the rocket engineers. And the lab itself, even at the time, they were like, nobody's going to call us the Rocket Propulsion Laboratory, even though that's what exactly that they were doing. It's called the Jet Propulsion Laboratory, even though that's not what they were working on. It should be called the Rocket Propulsion Laboratory, but it would have been a little bit like establishing the Teleportation Institute today. Nobody would take you seriously. So, but we're not working on the science fiction-y stuff, but in fact they were. And it was a very hard problem to solve. They had created rockets, both liquid fueled and solid fueled, but in the case of these JATO units to be attached to the planes, they couldn't, liquid fueled rockets take a lot more maintenance to store the fuel. But in this case, if you make solid fueled rockets, and we're familiar with them from bottle rockets or even fireworks, which is basically what they are, it's a much easier thing to store. Unfortunately, even though they could get solid rocket fueled rockets to work and have them work as JATO units, they weren't consistent. Sometimes they would work, sometimes they would explode. Not great. And so, but it was specifically Jack Parsons who figured out how to stabilize the fuel and made it possible to have JATO units to help the planes take off. And you could have these units, store them for a while, take them out, attach them to the planes, and they would help the planes take off with, on a very high success rate. So the Army wanted a lot more of them. Of course, the Jet Propulsion Laboratory was not even equipped to do mass production of anything. So they set up a new company, a company that still exists today. And of course, was it the Aerojet Corporation? Nope. It was and still is the Aerojet Corporation, even though their first job was to make these rocket assisted takeoff units, but we're not going to call it that. They're the JATO units for the Army Air Corps. And so many of the Suicide Club became executives at this new company. And the JATO success really showed how brilliant Jack Parsons was. I mean, nobody was able to solve that fuel problem, but he did. But he was also a very strange man. He was very much into the occult, and he used to do incantations before the rocket tests. It was actually called Devil's Gate Dam at the Uranus, and it's still there. And partly because of his occult tendencies, partly because he was more interested in the secretaries than the actual, running of the company. He was pushed out of the Aerojet Corporation. And then he sort of dabbled in many things and for a few years afterward, but unfortunately died in an explosion while making a special firework for a friend. And it became quite the Pasadena scandal, as you can see on the cover of the LA Times there. And again, he led a very interesting and strange life. I'm not going to go into all the details, but I really, the many twists and turns that his life took in and out of JPL were very interesting, particularly his occult tendencies. If you want to learn more about it, there's a book called Strange Angel. It's a biography of him. It's very interesting. But in fact, it was so interesting that the new CBS streaming service decided to make it into a miniseries. I know there's at least 2 seasons of it. If people are interested, you can see that. But one of the things was that Jack Parsons also, because he was so strange very often, and as things were becoming more reputable for JPL, they in fact decided to start erasing him, like literally erasing him from pictures and from the history of JPL. But of course, these books exist. Nobody's forgotten him, and people are a little bit more comfortable with paying tribute to him. But they say that you can never erase Jack Parsons from the history of JPL, because JPL actually stands for Jack Parsons Lab. As a bit of a joke there. Of course, if you want to learn more about his occult tendencies, you can look up a different book, and that one's called Sex and Rockets. So, leaving Jack Parsons aside as one of the many colorful people who went into the origins of JPL, JPL then became a center for the US Army to develop missiles, and they worked on many, many surface-to-surface missiles. And the German rocket engineers that were brought from basically the Nazi engineers who were brought in to help the US have rockets were primarily under von Braun working with the US Army. So there was a connection between the US Army's rocket group at JPL and the Alabama group, which was headed by von Braun. And so in 1957, the Soviet Union launched the first successful artificial satellite, Sputnik, and the US wanted to respond to it. And actually the first contract was given to the Navy to use one of their rockets to launch the first US satellite. Von Braun was very unhappy about that, and he kept pushing and pushing for the US government to allow him and his rockets to launch the satellite. And because he'd been working with JPL, he said, okay, we should build a satellite. And all of this started going on before they'd gotten the clearance. So von Braun did a long duration storage experiment with one of his rockets. So it was set aside. And they were working with an astronomer at University of Iowa, James Van Allen, and he started working on the satellite and an experiment to go on the satellite, again, even before the go-ahead had been given to JPL to create the satellite. And in fact, it was small enough that it was in the trunk of a car, and they drove it across country to bring it to JPL to put it in the rocket. And unfortunately, the very first rocket, the attempt to put the first US satellite in space failed. That was called Vanguard 1, and it just exploded on the launch pad. And of course, you can sort of imagine with von Braun saying, hey, I have this long duration storage experiment rocket ready, we can use that. And JPL was like, hey, we have this satellite we've been working on. And so they put it all together in less, in barely 2 months, they were ready to go again. But of course, they've been working on it longer than that. They were successful, they launched it. And that's the image that you see here. William Pickering was the head of JPL at the time. James Van Allen, who's the person who built the experiment. And as part of that experiment, we discovered the Van Allen radiation belts around the Earth, and that's why they named it after him. And Wernher von Braun, who built the rocket. And because of that success, NASA, Eisenhower formed the National Aeronautics and Space Administration, and JPL became a part of it as the main center for the robotic exploration of the solar system. So now we've gone from building JATO units to surface missiles to now switching over to exploring the solar system in space. And of course, the very earliest efforts were having to do with exploring the moon, because not long after the establishment of NASA, the charge was given to send human beings to the moon. But of course, you don't just send people to anywhere you haven't been to before. You send your robots to do the dangerous stuff first. First, there was the Ranger program built by JPL. These were flybys of the moon to get very good imaging of that. Then there was the Surveyor program, which they were designed to land on the moon and collect some more data. At some points, even people were, thinking, wow, you might, after billions of years of cosmic dust falling onto the moon, maybe there's this giant, layer of dust. And so if you try and land on it, you'll sink. And of course, when the landers landed, they could tell that that wasn't the case. Although there were other ways of even knowing that. Some astronomers already knew it based on infrared observations of the moon, based on how quickly it cooled and heated up. But still, the robots went there, definitively told us what the moon was like, which paved the way for then the astronauts to go. And in fact, Apollo 12 landed not too far from Surveyor 7, and they were able to collect bits and pieces of it to bring it back to Earth. And you can see those pieces and how they've been weathered on the moon over that time. And now, JPL became involved in multiple missions, and I'm sort of going to briefly go over these. And again, JPL was primarily doing the robotic exploration. JPL was not, it would help on various, instruments and different things for the human exploration, but that was not its main charge. And so there was a large number of missions that were sent to explore the solar system. And that was partly because of the mandate to go to the moon, which in fact, early on when President Kennedy wanted to send astronauts to the moon, that was really as a method to show that the US technology and capitalism and freedom were all better than the Soviet Union and communism and the totalitarian state that they were. But most scientists, in fact, in the US were poised to oppose that because they viewed it as a stunt. And in fact, they feared that there would be this massive diversion of money from science to this stunt. And so there was basically an agreement like, no, NASA won't be just doing this, one thing. We will be a science agency. We will do science. And a good deal of that science came to be done at JPL. And some of the missions, I'll sort of broadly go over the missions as laid out in the solar system. We've had missions to the sun. We've done a joint mission with the European Space Agency called Ulysses, which flew over the poles of the sun. There was a mission called Genesis, where it went and collected the particles of the solar wind and brought them back to the Earth. There was a mission called Stereo, where there were 2 spacecraft that would fly apart and give you stereo images of the sun, so you could get 3D in-depth information. Mercury, for the longest time, there was only one mission, and that was from JPL, Mariner 10 in 1973, that did a flyby. And we only, got a part of the image of what Mercury looked like. There was another mission headed out of the Goddard Space Flight Center, which is another NASA center, more recently, that gave us a much, went into orbit around Mercury and gave us a lot more information about it. But the very first one was from JPL. Venus, covered in thick clouds. Nobody really knew what the overall planet looked like until a mission called Magellan went and mapped the surface of Venus with radar, which could penetrate the clouds and give us the surface structure of Venus. And then one of the things that most people don't understand is, as much as we do exploration of other planets and things that are much further out in space, the primary planet that is studied by NASA and JPL is the Earth. We have more missions to the Earth than any other planet, which is appropriate. I mean, fundamentally, that's, hey, we all live here. And so it's one of those things that it's very important that we understand the Earth, but the techniques of studying the Earth, in fact, the instrumentation and the various kinds of scientific approaches are often the same as what you would study at other planets. So oftentimes we perfect things around the Earth, and then we can send those instruments elsewhere. But the fundamental reality of it is that what we have is a very complex system that we can study from space, which gives us a much broader bird's eye view. But at the same time, we can do in situ, what's called ground-based measurements. So we can always match up what's on the ground with space. And so they become very complementary, but also it gives us a better sense when we do the same thing elsewhere where we don't have the equivalent ground-based measurements. And we have various different missions. I particularly like the Aqua, Terra, and Aura missions. Aqua for water, Terra for land, Aura for air. But of course, those aren't the only ones that we study. But again, different parts of the Earth: land, air, water, clouds, and a whole slew of other missions, the Orbiting Carbon Observatory, and so on. So it's one of those things that JPL, either leading the entire mission or leading a critical part of the mission, has been doing, providing Earth observations for many, many, many years. And that is really the main planet that we study, and for good reason. The next one, which JPL in particular has been very heavily studying for many, many years, is Mars. And I'll go through some of the more interesting history of missions that we'd gone to. And I will say, and most people don't realize this, the most ambitious missions sent to Mars, as amazing as they are now, those are not the ones. In fact, Vikings 1 and 2 were the critical ones that were, in terms of ambition, were the most ambitious missions sent. And that was sort of riding the coattails of Apollo missions going to the moon. First, we had the various Mariner missions, which did flybys of Mars or went into orbit around Mars. And then you had Vikings 1 and 2, which there were 2 landers and 2 orbiters launched nearly simultaneously. So 4 spacecraft going there at the same time. And the orbiters were giving us great imagery. Vikings 1 and 2 landed there. They extended their arms to actually do measurements of the soil to see if potentially it was possible for life to have existed there. The conclusions were inconclusive, essentially. And so for many years, people were just yes, no, unclear. And then after almost 20 years, there was another mission that was sent called Mars Observer, which unfortunately failed. And then there was Mars Pathfinder, which was basically pioneering a new way, trying to be a cheaper way of going to Mars, which had the airbag landing and had this little rover, the Pathfinder rover, with it. And so that set us off on a new set of missions to Mars. And there were several, like the Mars Reconnaissance Orbiter, and various orbiters that went there and were successful. There was the Mars Polar Lander, which unfortunately crashed and failed. But then, using the basic structure of that one, the basic chassis, another one was built called Mars Phoenix that landed near the pole of Mars to sort of dig in and see whether there was what it was like, what the ice was like up there. And we could see that there was, carbon dioxide ice, but of course also water ice. Another mission that failed was Mars Climate Orbiter, but then we had other successful orbiters that have gone in. There's Mars Odyssey, Mars Global Surveyor. And then we had the Mars Exploration Rovers, 2 of them, the Spirit and Opportunity. which went in and of course lasted many, many years beyond their initial 90-day requirement, 1-year goal, and gave us an enormous amount of information about Mars, its past history, and the fact that there definitely was, we knew there was liquid flowing water in Mars in the past, and that potentially now, of course, there is, they verified very much of it, but in fact, there may be, thanks to some of these other orbiters, we've seen that there may be even slight liquid flowing water nowadays as these rivulets seem to come down the sides of craters. Whereas the Mars Science Laboratory Curiosity, that has been roaming around Mars for a while and has given us an enormous amount of information, again, about the past water history of Mars. And of course, we're interested in what water was like on Mars because, yes, life may exist in other forms, but fundamentally, what we're familiar with is life needs water, liquid water. And so that's why we're trying to trace the history of water so that it can have a sense for us of maybe there was at some point potential for life because there was so much water there. More recently, we've actually had the Mars InSight mission, which landed in 2018. It's an interesting mission. Again, it's the basic chassis of Mars Polar Lander and Mars Phoenix. So you're starting to get, because we now have a Mars program, you're starting to get cost savings because you can use the basic fundamental structures to do different missions. And InSight is basically senses vibrations from inside Mars. And so basically it's getting a sense when little meteorites hit Mars, these vibrations travel through Mars, and that gives us a sense of the interior of Mars, and that can tell us how Mars evolved. Why is it that Mars seems to have most likely had liquid water in the past? We've had very good evidence that that was the case, but it clearly does not have that now. To have liquid water on the surface means it had a much thicker atmosphere. Why did it lose that thick atmosphere? On the Earth, we have a very strong magnetic field. That magnetic field comes from a molten core, and that protects the Earth's atmosphere. That something changed about Mars, and that has to do with the interior, how the heat transport happens, and it clearly does not have as much of a molten core that can generate a magnetic field to defend its atmosphere and lost that atmosphere. So InSight is working on that problem of what is the inner structure of Mars. At the same time, we did a little bit of an experiment in terms of sending these very small satellites, as miniaturization as we've all come to enjoy with our cell phones. It was that there's a lot of technology that you can do, and these two small CubeSats were sent to Mars Cube 1, and to basically, their main effort was to demonstrate that we could build these and they could do a very specific job, in this case, relaying information from InSight as it was landing back to Earth, which they did very well. And it was a great success. Of course, the next rover to land on Mars, so InSight was not a rover, it's just a lander, but now the next landing will be for our second rover. The chassis, the basic structure of it is from the Curiosity rover, very big, it's about the size of a Volkswagen Bug. But now the experiments are different and the goal is different. Now, what we want to do is collect samples that, although the Curiosity rover has some equipment that it can do experiments on board to understand what the samples are, it's not clear that, I mean, it's never going to be as instructive as bringing the samples back to Earth. And that's the job that the Perseverance rover is going to be doing, is to collect samples from interesting sites and have them all together. And then a mission, not Perseverance itself, another mission will go there, grab those samples, and land on Mars, grab those samples, and come back and bring those samples back to Earth. So that one is still, being designed. But the other thing that the Perseverance rover has, sort of like the Marco satellites, is something, again, new and novel to be tested out. If it fails, it's okay. It's just a test. Is the named Ingenuity Mars helicopter. So the idea is that this is, very much the drones that we have today, but of course much lighter, because the atmosphere on Mars is only 1% the thickness of the atmosphere here on Earth. So you have to have the propellers turning enormously fast to give it the lift. And it has to be very light, but yeah, it solar charges itself and it can lift off. It has a camera and it can sort of broadcast information about what's around in a sort of much more close bird's eye view of the rover, and hopefully give us a better sense of, what's a good place to go in and take a sample. Again, this is much more of an experimental thing. If it doesn't work, that's fine. there's when you have a program, you can definitely do things and try things. There's a critical part of your mission that you want to accomplish, and that you have a lot of redundancy and a lot of effort to make sure. And then these are usually cheaper, and you're taking a lot more risks because it's not the primary mission. But so we've had a lot of successes at Mars. In fact, as of now, no other country, much less actually no other location, JPL is the only one that has successfully landed anything on Mars. And hopefully that success will continue with the Perseverance rover. But again, there's no guarantees. Space is difficult. The entry, descent, and landing is an incredibly difficult process. So just tune in next month, and hopefully all will go well, and we'll have another rover on Mars. And we will continue the trend of having Mars being the only planet we know of completely populated by robots. Jupiter was, again, biggest planet in the solar system, very interesting. But then multiple missions have gone there from JPL, the Pioneer program, the Voyager program, which had 2 spacecrafts. Ulysses actually went out to Jupiter to be flung back to over the pole of the sun, but then it studied Jupiter along the way. Cassini-Huygens was a mission to Saturn, but it swung by Jupiter, so it gave us a lot of information there. The Galileo mission orbited Jupiter for many, many years and had a probe go into Jupiter to study the content underneath the top layers of the atmosphere. And of course, there's another mission now from JPL called Juno, which is orbiting Jupiter, and it's going over the poles of Jupiter. And if you go to the images, the poles have very, very interesting dynamic cloud structures, something that was not expected at all. Saturn was the next mission. In fact, the Pioneer 11 mission flew by Saturn. Voyagers 1 and 2 flew by Saturn, again, to give us incredible imagery and great study of the satellites. In fact, both for Jupiter and Saturn, oftentimes their satellites are far more interesting in many ways than the planets are. Both Jupiter and Saturn seem to have moons that have under ice oceans. And so potentially there might be some life on, potentially on Europa or on Jupiter and one of the moons of Saturn. Which again have these ice that have cracks and these geysers that seem to be coming up. Cassini-Huygens orbited there and studied them for many, many years. And the Huygens probe actually went into another moon of Saturn called Titan, which has a very, very thick atmosphere. And in fact, its atmospheric thickness is as much as the Earth's. And it was the very first time that we landed. This was a European probe that was being carried on the American mission, and so studied what was the surface of Titan-like, and it looks like it has lots of liquid, but it's not liquid water, it's liquid ethane and liquid methane. And finally, the only missions that have gone out further to study planets from JPL are Voyager 2, which continued on from Saturn to study Uranus, and then continued on to study Neptune. No other missions have gone there. There was another mission, New Horizons, which was not from JPL, but from the Applied Physics Labs, along with Goddard Space Flight Center, which went and studied the dwarf planet Pluto. So if you saw the images from Pluto, that was an amazing mission from there. But JPL has also studied dwarf planets. In fact, we developed it into, even though JPL started with jet propulsion, which was not even jet propulsion, but in fact was rocket propulsion, they came up with something that had been really science fiction, again, connecting up with this idea, that bizarre idea that, these are science fiction-y things and you shouldn't work on them, and they worked on them and they made rockets work. And then this other one is ion engines, where you take a gas, you ionize the particles of the gas, you put it in a magnetic field so that it has ionized particles are, once you've stripped the electrons off them, they're positive. So you put it in a positive field, like charges repel. So you get these constant stream of positively charged particles that are being emitted. Now, the amount of thrust that you get from that is tiny. You're not going to use that to take off from the Earth. It can't, it's not going to do anything. But once you're in space, once you have a rocket put you in space, you can use your ion engine because there's no friction in space. So even though the force on the spacecraft is the force of a piece of paper on your hand on the Earth, but that force is constant. And in fact, you can do things which you would have never been able to do with chemical rockets, which is you can go and get yourself into orbit around an asteroid, like which was Vesta, and then you can do something which, again, in science fiction and in Star Trek, break orbit, Mr. Sulu, we've just gotten too used to that, but doing it with chemical propulsion, that is very difficult because it weighs a lot and you have to have huge rockets and so on. But with ion engines, you trade that for just time. So you go into orbit and you have a very weird orbit and you use your ion engine to become more circular. And then when you want to break orbit, you start firing your engine and you're spiraling away and away, and eventually you break orbit. And then it went around the dwarf planet series, went into orbit and orbited it for many, many years and studied it in a way that had never been studied before. So these ion engines have provided us something that we only expected from science fiction, but in fact, this is entirely reality, and it provided us something that we could not do. And of course, there's comets that we've studied. There was a comet sample return mission called Stardust, where it collected samples from the tail of a comet. Then there was the Deep Impact mission, which we slammed something into a comet so that the interior stuff would spill out, and then we'd study what the interior stuff that it came out. So we're not looking at essentially at the weathered stuff on the outside, but what the more pure, pristine stuff within the comet. The Voyagers actually continued and now have passed what's called the heliopause. That is, you have this solar wind of particles that are coming off the sun, and then they impact as it creates this bubble, but as the sun is going through what's called the interstellar medium, which is the gas that's within the rest of the galaxy, and you get this basically this bow shock. And so they have now passed the bow shock, both for Voyager 1 and Voyager 2. So now they are in interstellar space. They're studying what is not the material or the gases that are dominated by the sun, but the gases, the magnetic fields that are dominated by the rest of the galaxy with stuff that's in between the stars. But we, of course, JPL never stopped there. We can't go to, other stars, much less other galaxies, but we've had a very robust astrophysics telescope projects. The very first space infrared observatory came out of JPL. It was a joint mission with the United Kingdom and the Netherlands called the Infrared Astronomical Satellite. We have another one called the Wide Field Infrared Survey Explorer, which is still, it was launched in 2009, and it did its main survey of the sky, but then has continued surveying at two of its shorter wavelengths in the infrared to look for asteroids, and particularly near-Earth asteroids, which potentially could impact the Earth. So that is still functioning today. But we don't do just X-ray. There's the Galaxy Evolution Explorer, which was an ultraviolet telescope, which launched in 2003 and lasted for many years. There's the New Star X-ray telescope. It used new technologies to make more compact X-ray observing telescopes, and was launched in 2012, and it is very much functioning today very well. But then finally, what you see floating behind me was the mission that I came to JPL to work on, which is called the Spitzer Space Telescope. It was launched in 2003. We just retired it about a year ago, and it gave us an enormous window into the universe, because in the infrared light penetrates areas where you wouldn't see in optical or ultraviolet light. So I used it to study supermassive black holes at the centers of galaxies. Other people used it to study young stars forming, because they often are enshrouded in dust. People study the furthest galaxies. People study the nearest failed stars called brown dwarfs. So and then there's an enormous amount of studies that were done for solar system objects, for comets and Kuiper belt objects. Those are objects that are sort of around the orbit of Pluto and so on. So it was an incredibly successful telescope, and it was a very great privilege to have worked on it. I was not a party to building it. It was already almost finished when I started working at JPL, but I was very happy to be able to use it for the scientific purposes that I was interested in, as well as thousands of astronomers across the world were able to use it. So that was a great success to come out of JPL. So one of the things I was asked to do also was to mention that for those who are undergraduates or graduates, or who are educators, JPL has a very strong intern program. So you can go there and look at the various different kinds of internships that are available for you if you want to join, if you're an undergraduate student or a graduate student, or like I said, a non-traditional educator, museum folks, and so on. So you can become a part be a party to JPL and go to the education site. You can look at the internships or various other opportunities. Otherwise, I think I will stop there, and I'd be happy to take the, as I can see, multiple questions that have come up. So.
Yeah, great. Well, thank you, Varoujan. I guess we will have this slide shared here for a few moments, so people may want to extract useful information from it. But there are several great questions saved for you. The first one is from Sean Broadhead, asking how many other countries have sent spacecraft towards Mars?
That's actually an interesting question. For the longest time, it was only originally the Soviet Union. In fact, they did the first landing on Mars, but we don't call it a successful landing because they really didn't get any data back from the mission that they landed. There was clearly a successful landing. They got some signals, but then it failed. The United States did that, and those were the only two countries for the longest time. In terms of just for landing or orbiting. And then the European Space Agency has sent a mission called Mars Express, and it's still orbiting and functioning. And then the Indian Space Agency has now sent a mission to Mars. It's called the Mars Orbiting Mission, MOM, and that's been a successful mission as well. There is, I don't want to get the country wrong. There's one of the Gulf countries, I want to say the United Arab Emirates is going to be sending a mission to Mars. As they used the idea of building a satellite for doing something very difficult as a way to start building up their technological capabilities. And I believe China will be sending mission to Mars as well. But right now, the main countries that have sent missions to Mars, again, being the primary missions, they're usually, for example, we collaborate with European countries that built various bits and pieces of instruments and so on. But in terms of the lead country and the lead mission builders, it's been the United States, Soviet Union, the European Space Agency, and India.
Great. Thank you for the elaborated answer, Varoujan. The next one is from Caleb Liu asking, is there snow on Pluto?
Yes, it's interesting in the sense that, Pluto is covered with a lot of icy things, and then part of it is water ice, which is the kind of snow that we're used to. But a lot of it is other kinds of material which have now become ice. There's methane, which is the stuff that comes out of your a gas stove, but then if you cool it enough, then it will become like frost and ice and freeze up. So yeah, and these outer planets, particularly for Pluto, it's a dwarf planet, but certainly the moons of Uranus and Neptune, you have these various different kinds of ices. And it's just a matter of what the temperature is. But even on, for example, Mars is cold enough that it has both water ice and carbon dioxide ice. And if you want to see what carbon dioxide ice is, we just call that dry ice. you go to any Halloween event and you see all that bubbling stuff, that's carbon dioxide ice. So it's just a matter of, is the temperature there and is the material there? And there are very many different kinds of ices. But water ice is very common. And so because the atmosphere tends to be thinner, it doesn't go into a rain phase. There's no liquid. So once things warm up, it's sort of what's called sublimates. And then some of it then can refreeze as frost and ice and snow.
Yeah, great. And the next question is from Stephen Schreier, asking, is there a replacement for the Spitzer infrared telescope?
So not exactly, but so there was, you may have heard about this, there's the James Webb Space Telescope, which is in fact in many ways the successor to the Spitzer Space Telescope. It has many wavelengths in common with the Spitzer Space Telescope, but it has many wavelengths in common with the Hubble Space Telescope. So it's sort of this bridging the gap between the two, but it is primarily an infrared telescope like Spitzer. Spitzer had a much wider wavelength range that it covered, but still a large portion of the wavelength range of the James Webb Space Telescope, which will launch this year, is in the infrared. And in many ways, James Webb is the successor. There's no identical successor, but that's the closest one.
Thank you, Varoujan. And Megan Edwards was asking, do you think commercial enterprises will encroach on JPL science, like SpaceX taking over Earth to near Earth orbit?
That's a real worry that we have. On the one hand, one of the things that's great about SpaceX is it's making going into space cheaper, which means we can spend more of the dollars for any mission on the science and the science instrumentation and not on the rocket to get us there. And that's always been very expensive, and that's always been a big chunk of the cost. The fact that SpaceX and other rockets have brought that cost down, they're expanding the science that we can do. Great. On the other hand, with unfortunately these constellations, they're great in terms of providing internet to areas of the Earth which are not ever going to get internet. You're not going to draw cables there, and even satellites aren't easily, if the satellites are providing them internet, it's usually very slow. But this is much faster, much better internet. But for ground-based astronomy, it actually makes life a lot harder. Because you have a lot of these objects that will be going through. SpaceX has worked a little bit on, initially they didn't even work on this, but now they've worked on mitigating the reflectivity of those satellites, which is very welcomed by the astronomical community. The question is just how many will be up there. But strangely enough, specifically about how it affects JPL, we do space missions. Generally, we have ground-based support. But in reality, I mean, it's much more of an impact for ground-based astronomy, which is, our biggest telescopes on the ground are on the ground because that's, the cheapest, lifting a giant telescope into space is going to be very difficult, but it's going to interfere with that. The missions themselves, overall, not really.
Yeah, that makes sense. And then next question from Greg Ewing. There seems to be renewed interest in Venus long after the early Soviet missions. What does Venus have to teach us?
So Venus is a very, very strange planet, and it's an incredibly hostile planet. And if you want to win a bar bet, usually if you go around and say, okay, tell me what's the hottest planet in the solar system, almost everybody will say, well, Mercury is the closest. They'll bet on Mercury, and you say, aha, no, Venus, and you'll win your bar bet and win a beer. But the reason Venus is the hottest planet, even though it's not the closest planet to the sun, which seems counterintuitive, is because it has a runaway greenhouse effect. So Venus clearly had, or something happened so that it has an enormous, thick, cloudy atmosphere made primarily of carbon dioxide. And so we're worried very much about carbon dioxide here on Earth as a greenhouse gas. Imagine it all being greenhouse gas, or mostly being greenhouse gas. So it's incredibly hot. And the Soviets were actually the only ones who were successful to actually land any spacecraft on the surface of Venus. Most of them failed, but a couple of them didn't. And we got these images from the surface of Venus. And then the radar map that was provided by the Magellan mission gave us a surface topography of Venus, which is very different. It's very flat in many ways. It's not that it doesn't have hills or valleys, but not at the difference in height that we see on Earth or on Mars. So the history of Venus will definitely tell us something about how the planets evolve, but more importantly, also what happened to Venus. Venus is almost identical in size to the Earth, and it's not that far from the Earth as well. So chemistry-wise, most likely it had similar chemistry, but what made it the hellhole that it is? Because if there's any place on Earth, and I'm quoting Carl Sagan on this one, if there's any place in the solar system that resembles our sort of classical view of hell, it's Venus. It's super hot. The pressure, the atmosphere is so thick, it just crushes almost everything. And the atmosphere is left with sulfuric acid. So in fact, the cameras that they flew on the Venera spacecraft, the Soviet spacecraft which landed, they couldn't be made of glass, because if you ever know about etching glass, is you use sulfuric acid. So as soon as the lens popped off, they would have just fogged over. So they actually had to use diamond lenses so that they could take these images from the surface of Venus. So it's incredibly hostile. But how did it become that compared to Earth or even Mars, even though Mars has changed? So how did it start? How did it change? And why is it the way it is now? That tells us both the history of planetary formation, but also something about runaway greenhouse effects, which we certainly don't want to get there. And I'm not saying we're definitely going to do that, but that's certainly a cautionary tale sitting right next door.
Yeah, totally. And the recent discovery of a potential biosignature gas on Venus also, just reignite the interest of missions to Venus. I guess it's not as dead as we previously thought.
Yeah, no, I mean, that's something that people had actually, I don't know if they had thought about it on Venus, but people had speculated that Jupiter might have life in its clouds, that it would be, again, go back to the original Cosmos book from Carl Sagan, that if you just wanted to use speculation, potentially that you could have life that evolved in the clouds and lived in the clouds and so on. And this biosignature, again, it's new and it'll have to be, verified over time. But my God, I mean, if that's the case, oh wow, that's an entirely new way of studying potential life in our solar system, and that isn't anything we would have thought about even a year ago.
Yeah, totally. And I have two more questions here. One from Oclot 714, asking what would be the current technology that we would view the way people viewed rockets during Jack Parsons Day?
Yeah, that's a little bit difficult, but I think there's sort of a couple of areas that people are working. I don't know if there's anything that's quite as in that area, because if I say it, then somehow I'm saying that it's disreputable now, but it will become reputable later. No, I mean, there's no guarantee that that's the case. But I mean, there are some things that are more speculative, or certainly more, future oriented, but certainly not, something that we're going to be doing now. There's certainly people who are working on solar sails, which catch light from the sun. It's this giant thin membranes which are being pushed by the sun. And then on top of that, you can have, a giant laser from the Earth pushing on that, so that you can actually push something to go very far, very fast. But again, that's not, disreputable. Everybody thinks that's workable. I think the closest one maybe, and this came up even early on in the 50s and 60s, is the nuclear propulsion, in the sense that you actually have like nuclear weapons exploding behind your spacecraft, giving you your thrust. That's one way. There's this other thing that people have thought about, using the 0-point energy of space, and that's been very speculative about this one particular kind of drive, and I can't quite remember the name of it, but that one, again, it's not even clear that it provides any thrust. Some people say yes, some people say no. Nobody knows how it really works. There's some speculation, but again, right now it's in this very weird in between, but people have taken it more seriously than they did rockets in the past.
Yeah. Oh, I left out one more question. So there are two more, and I guess we could maybe talk about them in the last 3 minutes. So AC asked, could robots build a radio telescope on the far side of the moon to replace the collapsed Arecibo telescope?
So generally speaking, putting a radio telescope on the far side of the moon has always been viewed as a great idea, mostly because now the Earth is very radio loud, just radio noisy. I shouldn't even say radio loud. It's radio noisy. There's lots of radio waves from cell phones and whatever. So there's no clear channel to view the sky, and you always have to constantly filter out all this other stuff. But the moon itself is a pretty good blocking of the Earth's noise. And so if this is the Earth, you have the moon behind it, with the moon blocking for you, you can get enormously quiet skies to look at. That's great, except, and this goes for optical telescopes as well, it's so much easier to build and maintain something on the Earth than it is in space or on the moon. So each one has its advantages. You can build or rebuild Arecibo on Earth. China has now built even what was larger radio telescope than Arecibo. And in that way, you have huge advantages just because it's here on Earth. You can go to it. You can, in particular, changing instruments that, imagine sort of changing the detector on your phones. I mean, we change phones to do that, but for telescopes, you don't do that. You keep the same telescopes and you change the cameras, or in terms of radio telescopes, you change the receivers, and you can constantly upgrade them to become more sensitive or do different frequencies or wavelengths. So that advantage is something that ground-based observatories will always have over space-based or even on the moon. But the moon does provide this incredibly high sensitivity that you can get, that you just are not going to have on the Earth.
Yeah, that makes total sense. And one final question from John Liani asking, what would be preferred, an ion engine or solar sail propulsion for the interplanetary voyages?
So for interplanetary voyages, you really are much more in the solar sail region than you are an ion engine. Ion engines, at some point, you need something to help you ionize whatever fuel you're carrying. So even if you could carry a large amount of fuel, these are called solar electric propulsion. That is, you have solar panels, you receive the light, you convert that to electricity, you use that electricity to ionize the gas and then push it out. Already, by the time you're getting around to Jupiter and Saturn, the sun is very faint, and the Juno mission is actually solar powered, but its solar panels have to be the size of basically you can park a bus on them to get enough light at Jupiter. This is called the inverse square law. You go twice the distance, you get 1/4 the amount of light that you're getting from the sun. So it becomes very quickly diminishing. In terms of solar sail, one of the advantages is that it's a very light system. You're not carrying any fuel, and you certainly accelerate. And of course, as you get further out from the sun, but then you're not going to get as much push. But then there's the solar wind. These are particles that are coming off the wind. There's not just the photons, not just the light particles, but physical protons and that are coming off the sun. And so those can still push you a fair bit. And on top of that, then you can still have this laser based on Earth or somewhere in space that's just sitting there being powered much closer to the sun and just throwing some photons along your way to push you further out faster. But again, the inverse square law always works against you. But again, the solar particles are something that can still help you out. So and there's a group now that's working on tiny solar sailed spacecraft with tiny spacecraft attached to them to be accelerated by lasers from the ground so that they could get so fast so early, because that's the other advantage, is that you can dump an enormous amount of photons now, and because there's no friction, it's not going to slow down, to direct them towards a nearby star, so that within, I don't know how long they're expecting, 30, 40 years, but again, much faster than we would have ever imagined, you can get there. And that's solar sail has that, because again, you not only just use the sun, but you can artificially dump a lot of photons on them, while for the solar electric propulsion, that's really is not the case, particularly because again, the further you want to go, you still need to carry the fuel.
Yeah. Well, thank you very much for sharing your thoughts, Varoujan. And those are all great questions. So I'm personally also very excited that we're making all these progress in space exploration. So I guess this concludes our lecture today. I'd like to thank everyone again for joining us this evening. And I hope you all enjoyed the lecture and learned something very interesting. Let's also thank our hardworking volunteers again here. Big claps for them. So we will be sending out a survey in a couple of days to everyone registered just to collect feedback. The survey is completely anonymous, and we will only be seeing the statistical results. So having the evaluation will greatly help us keep running this kind of outreach events, both virtually and in person later. So we would really appreciate your taking a few minutes to complete the survey. And you will also get a chance to sign up for our email list in the survey. So our next Cosmic Thursdays will be on, and again, a Thursday, March the 4th, and it will be about the monstrous supermassive black holes in the universe. So if you would like to be informed on our upcoming events, either sign up to be on our email list, or you could follow us on our Facebook page, which is UCR Astronomy. And I can also post the link in the chat right after this. So thank you everyone again, and I hope you have a good night.
Bye.
Bye.
So long, everybody.
Bye everyone. Take care.